Hi everybody, this is the second and final lecture from chapter 4 in your textbook. This has to do with the curvature and refraction of the Earth and how to deal with the correction for those two factors. So there are two slides from the last lecture that we looked at, and the first is this represents, point A represents where you've placed a level, and point D or point H represent where you've placed the rod. And the first shows from the curvature of the Earth the fact that if you put your level here, even though these are at the same elevation, because the Earth is curved, that the level will be essentially lower, or the level reading will be too high. So for that reason, we need to correct for the curvature of the Earth. Now, the next part is, shown over here on point H, is that light actually refracts and makes the object higher than you would expect it to be. That's shown sort of here. In other words, if you look straight out at the sun, for example, the sun will actually be lower than where you see it in terms of looking through the atmosphere of the Earth. So there's a change in height that is a curvature and refraction change that we need to correct for. Now, both of these are based on the distance between the level and the rod. So if you balance your backside and your foresight, if you're doing a differential level like we will be in lab number 5, then you don't have to take this into account. But if you have to do a short foresight and a long backside, you need to take the correction into account in order to get accurate elevation changes. So I've sort of summarized what's going on with this in your textbook because it can be a little bit confusing. So this is the material in your textbook in chapter 4 on approximately pages 73 and 74. But the basic information is that the Earth's curvature and the refraction of light through the atmosphere create an error in readings that change elevation. And as I said just now, the error can be eliminated by balancing or nearly making equal in length the backside and the forward side. But sometimes that's not possible. Sometimes you have to, you have an object that you need to get an elevation difference between, and you can't set the level up midway in between. Now, it's also important to note the Earth curves in all directions. It's a three-dimensional curvature, so you don't have to do a backside and a foresight that are 180 degrees apart. You can backside and forward sight at different angles, and if you can balance the backside and the foresight, you're still not going to have to worry about this correction. But when you do have to worry about the correction, the curvature of the Earth makes the object on a level line lower, and the refraction makes the object appear higher. So they work in the opposite directions like the other slide showed us. But the refraction effect is about 1/7 as great as the curvature effect. So curvature kind of trumps this correction. But the good news is they're both based on distance between the level and the rod, so we can combine them into a single correction. So having said that, we need to do one correction if we're using SI units and one correction if we're using US customary units. In US customary units, we base the correction on capital F, which is thousands of feet. So in this example, if the distance from the level to the rod is 5,000 feet, F is equal to 5. And it can be a decimal number as well. So in other words, if it was an even mile, if the distance between the level and the rod was 5,280 feet, capital F would be 5.280. In SI units, we just base it on capital K, which is kilometers. So here I have the correction if we're in the metric system. You take the value, the number of kilometers between the level and the rod in kilometers. So if it's in meters, you would divide that by 1,000. But the number of kilometers squared, then you multiply that number by 0.0675. And that will give you the correction. And it's important to note, I didn't note here, but that correction will be in meters, not in kilometers. So let me write that out here. I need to change the font here so I can get rid of that superscript. And I'm going to say the correction will be in meters. And if we're using U.S. customary units, we take the number of thousands of feet. In other words, we already take the number of feet divided by 1,000. We square that number, and then we multiply it by 0.0206, and that will give us h sub f. And the correction here will be in, and change my font, the correction here will be in feet. And these numbers tend to be quite small. And it makes sense, doesn't it? I mean, you don't really expect there to be a huge correction based on curvature and refraction. But over the course of, 5,000 feet, a mile or so, you might get a correction of a foot. So that's an approximate. It increases exponentially because we do square that number. So the further your distance, or the further the unbalanced backside and forward sight, the larger the distance, and it's not linear. So a 2,000 foot correction is much larger than a 1,000 foot correction. It's not just double. All right, so sort of to summarize this, the curvature is always the biggest factor, and so the curvature always makes the rod reading too high. So any correction is always subtracted from the rod reading to give you the actual change in elevation, whether that change in elevation is between the instrument and the rod or between two readings. And the other thing to remember is the correction is always larger on longer distances. So if you have a short sight and a long sight, the long sight will be the governing body of this correction. All right, everybody, so that should get you ready to do your homework. And if you have any questions, make sure that you let me know. We'll see you in class.